Hello, hello everybody. This is Ritesh. Today I'm going to talk about our recent work that got published in this year's VLDB 2023. The work is on a self-training algorithm that improves the level efficiency of current state of the art for information extraction from semi-structured web pages. So this work is a joint collaborative effort with my colleagues in Amazon. So before I go over our contributions, let me give you a little primer about the task itself. So we tackle the web information extraction task in this paper, where we are essentially asking the question, what are some of the key information appearing on a semi-structured web page, and can we extract those information like extracting key value pairs that appears on that web page automatically. So we will be in this task, we will be given an input of a semi-structured web page and a list of attributes that we want to extract. If you look at the example on the right, we might be interested, for example, in some key information such as when was this movie released, who was the director, what genre it was, what runtime it was, and so on and so forth. And as you can see that all this information does appear on the web page itself from the human annotation. As an output of this task, we would require that the model returns the corresponding text for each attribute and the XPath of the DOM node in the HTML structure where this text appears. So before we move on to our before we move on to our contributions, what are some of the existing solutions and what are their limitations? So one of the go-to approaches for web extraction in enterprise scale has a long been wrapper induction, where some XPath-based rules or wrappers are first constructed from some human-level samples, and then those wrappers are applied one by one on a semi-structured web page to extract key pieces of information. Now, the problem with this approach is that it is hard to scale up when we have thousands of websites with diverse layouts. It needs more human effort to adapt to recent changes in the page layouts, and also sometimes needs some upkeep and maintenance to be done to make sure that we have the layer wrappers that are up to date with the recent changes that a website may make. Now, a potential solution to sort of automate these automate and catch up to the changes in a wrapper induction way is to learn how to post edit as a wrapper from a human, learned from a human level sample using spatialized annotation tools and expert annotators. But the problem with this approach is it requires a lot of iterations, requires specialized softwares, and also requires high inter-annotator agreement, which typically takes a lot of time to converge on. Now, one way to sort of go beyond this and sort of automate the process of web extraction is to take a model-based approach where we feed a model, for example, say a machine learning model on some features of key pieces of information that we might want to extract from a human level samples. Those features could be, text features, could be visual features, could be layout-based features or HTML structural features, and we feed a model those features from the human level samples, train the model on those features, and finally, once we have trained them, we use them to infer the key pieces of information we're interested in, the attributes we want to extract from the test set of web pages. But the problem with this approach is the current state of the art models used for web extraction are typically larger models and they are data hungry, which means that they are not very level efficient. They do require a lot of human level samples to converge and give us the performance we are looking for. So what solutions exist in the machine learning literature to circumvent this? So to improve level efficiency, a typical solution that usually works well for web information extraction is transfer learning, where a machine learning model is first trained on a bunch of seed websites, which has a lot of human labeled web pages. It's first pre-trained on those human labeled pages from seed websites. Then once that pre-training is done, we continue fine-tuning the model on a few human labeled pages from the target websites. And finally, we use that fine-tuned and pre-trained model to infer the key pieces of information, extract the attributes we want to extract from the target web pages. But here is the problem, though, that it is true that transfer learning does reduce leveling cost, but as you can see, as I have in this brackets here, to some extent. So why it does it reduce leveling cost to some extent? Because although it does reduce the leveling cost from the target websites, it sort of relies on having a representative set of exhaustive corpus that composes of thousands of diverse web pages from each seed website to pre-train the model. So it essentially transfers the labeling cost from the target websites to the seed websites. Now, labeling a representative set of web pages from a diverse set of seed websites is an expensive ordeal. Websites typically host structurally unique page layouts, even though their page renderings can often appear similar. Now, one follow-up question that one might also ask here is using large language models could be a solution here. And we actually agree that it can be, but it cannot be used off the shelf or out of the box, as our experiments have shown. We see that large language models are great generalist models with excellent few-shot capabilities, but their performance on complex visually rich documents like web pages typically scales with the number of human label samples that are being used, either to demonstrate how to extract information from these complex documents or fine-tune them, or the number of trainable model parameters that it has. Now, getting a larger model is not always a practical solution in an enterprise scenario. And getting more human level samples, converging on the quality of the annotation, getting a high interpreter agreement is already expensive, as we discussed before. So what we want based on this literature survey is three things. One, we want good scaling properties in our wave extraction model, which means that the solution should generalize for models with different sizes and shouldn't just rely on more data or larger model to have competitive performance. Second, it should be cost effective, which means it should reduce the cost of leveling from both seed and target websites. And third, it should achieve A and B without actually affecting the model's end-to-end performance. So with these tenets in mind, we introduce our current work, which is called Level Efficient Self-Training for Web Extraction, or as we call it in short, LEST. So what are we proposing in this work? What we are essentially proposing is a self-training algorithm. We are proposing a self-training algorithm, a generalizable self-training algorithm that can be used for web extraction that only leverages a few human level pages from both seed and target websites to train a model. We will show that it does follow the tenets of generalizability and scalability. And when we use a list to train a backbone model for web extraction, it does outperform state-of-the-art models that has been open sourced by industry leaders by up to 23 F1 points on zero-shot extraction scenarios, which means that it does not lose performance points just to save cost in terms of human labels. In terms of label efficiency, we also see that using list can save up to 11 times of human label samples that is currently needed to obtain comparable performance as our models using naive transfer learning. So this is a huge cost saving in terms of human effort as well. So as we said before, our core contribution of this work is a modified or enhanced self-training algorithm that improves the model's extraction performance and reduces its level cost or the number of labels it requires to train a model. So before I sort of introduce those enhancements, here's a little refresher on the self-training algorithm and how it works on a web information extraction paradigm. So self-training algorithm typically starts with training the model, which is called the teacher model, on a few human labeled pages from the target website. Once we have the trained model, we assign the model as the student model, which is a model with the same architecture as the teacher model, but it's trained on a different corpus. So to construct the corpus to train the student model, two things are done. First, we augment the human label samples that was used to train the teacher model, and we assign some pseudo labels to some unlabeled web pages. So these unlabeled web pages are assigned pseudo labels by the teacher model itself, which makes an inference call on the unlabeled pages to construct the pseudo label samples, and then the pseudo label samples along with the human label samples are used to train the student model. Once the student model is trained, we assign it back as the new teacher model for the next iteration, and this back and forth goes on till we have a convergence on both models, where the training algorithm terminates. Now, self-training, sort of translating this paradigm of self-training in the space of deep neural networks is not straightforward, especially when the number of human label samples is quite low. Why? Because of two reasons. One, when we use vanilla or naive self-training to train the teacher model using only a few human label samples from scratch, we see that the model itself does not converge very easily. It is typically underfit, and the quality of zero label samples it generates when it constructs the training corpus of the student model can be quite noisy. Now, if I train a student model on these noisy samples, it is highly likely that the quality of the model will easily degrade and we will have a lower quality model at our hand. So to address these issues, we introduce two things. First, we introduce the paradigm of data programming to generate higher quality pseudo-level samples using multiple generative sources than relying only on the teacher model that are complementary to each other. And finally, we introduce a noise ourselves training that accounts for potential noise in the student training corpus and amplifies or damps the training signal received from that particular signal sample based on that level of noise. So in terms of efficient data programming, we use two generative sources. One is the backbone model used from the previous training iteration, which is the teacher model itself. And the second is the supplementary semi-supervised, a supplementary semi-supervised generative model that complements the teacher model itself. The semi-supervised generative model uses two sources of supervision. One is the weak supervision, and another is an existing open source work called Weir, which encodes overlapping attributes by clustering wrappers. We will not go over more details about the semi-supervised generative model itself because of the limitations of time, but more details are given in our paper itself. Now, moving on to the second contribution, the noise hour training, the way we design it is we essentially assign a probabilistic weight to each sample in the pseudo level corpus that is used to train the student model, where we assign higher weights to less noisy samples and lower weights to more noisy samples. Based on these weights, we amplify or dampen the training signal received from each sample in the training corpus when we compute the loss over the training set and train the model accordingly. So this is an end-to-end workflow of our algorithm. More details are there in our paper. To sort of go quickly over the experiments that we ran, we performed experiments on two publicly available datasets, SWDE and WebSRC. For both datasets, our objective was to extract a set of predefined attributes from a web page. If I look more closely at the SWDE dataset, it contained 8 verticals, and the WebSRC dataset contained 10 verticals. Each vertical contained thousands of web pages on covering a particular topic like auto, movie, university, or different job sites. To establish the generalizability of our algorithm, we experimented with two backbone models called Symptom and Markup LM, and we experimented by training both models using our algorithm. We trained our model by using web pages from two seed websites, where we only used 9 human label pages from each website to construct our training corpus and train the models. The rest of the web pages were unlabeled and were assigned a pseudo label using our generative sources. Now, if I compare the performance of these backbone models trained using LEAST, we see that in terms of zero shot F1 score, where no human level pages are used from the target website, we see a 23 point jump in the F1 score compared to the baseline that does not use our algorithm. And if I introduce five human level pages from the target website in this 5-shot scenario, we also see a huge improvement in our performance, which indicates greater scaling properties of our algorithm as well. Similar things are seen for the markup LM model itself, where we see better performance in the zero-shot scenario and good scaling properties in the 5-shot scenario as well. In terms of human level efficiency, we see that where our least trained model Symptom and Markup LM uses only 18 human level pages and assigns pseudo labels to the rest of the pages, filters them and trains the model on themselves. To get similar type of performance on the zero shot scenario using naive transfer learning, we would require much more number of models, much more number of human level pages to construct our training set. For Symptom, we would require almost double the number of human level pages to achieve the same level of performance. We have more experiments and results that discusses the scaling property of our algorithm in details, and discusses different ways to analyze the results, as well as various ablation studies, which we will skip in this presentation for now. So if I want to summarize the results, what we see is that our results show that LIST generalizes to multiple state-of-the-art models, which have been made publicly available. And we show that our model performs well on publicly available benchmark datasets. We see that we outperform state-of-the-art models by up to 23 F1 points and save up to 11 times more human level samples, essentially making the human level cost a 1/10 of what was needed before to achieve similar performance as ours. So this has been our presentation, please do check out our paper, and thank you so much for listening in. Thank you.